In July of 2022, an astronomer in Australia opened up the first deep field data from the James Webb Space Telescope. He was doing something routine, measuring the brightness of galaxies, estimating their masses, tools he had used hundreds of times. The numbers came back wrong. 6 galaxies, in a region of sky less than 2 months old to JWST observations, appeared to contain as much stellar mass as the Milky Way does today. Possibly more. Observed at a time when the universe was barely 500 million years old, 5% of its current age. He ran the calculations again. Same result. He called his collaborators. What he told them, in a quote he would later give to a journalist, was this: "We just kind of looked at each other and said, is this real?" The paper they would publish in Nature in February of 2023 would set off 3 years of intense debate. Headlines proclaiming the Big Bang had been broken, and a slow, patient process of figuring out what JWST had actually found. By the end of 2025, the picture had clarified, but not in the way the headlines suggested. July 2022. NASA Goddard Space Flight Center, Greenbelt, Maryland. The James Webb Space Telescope has been in science operations for less than 2 months. The first deep field images, the ones released publicly on July 12, to enormous fanfare. The ones that showed thousands of galaxies in a patch of sky, smaller than a grain of sand held at arm's length, are now in the hands of researchers around the world, being sliced apart, analyzed, measured. Ivo Labbé is one of those researchers. He is an astronomer at Swinburne University of Technology in Australia, and he is doing something that sounds routine. He is measuring the brightness of objects in the deep field at different wavelengths of infrared light, a process called photometry, and using those brightness measurements to estimate how massive the galaxies in the image actually are. The process is standard. The tools are standard. He has done this hundreds of times. The number he gets back is not standard. He is looking at a group of objects, galaxies selected from the first JWST deep field data, because their colors suggest they are at very high redshift, meaning very far away, meaning he is seeing them as they existed very early in the history of the universe, when the universe was 500 to 700 million years old. The stellar mass estimate, the number that tells you how many stars are in the galaxy, how massive it is, comes back wrong. Too large, much too large. One of the galaxies appears to contain as many stars as the Milky Way does today. Possibly more, seen at a time when the universe was barely 5% of its current age. Labbé runs the calculation again. Same result. He checks the redshift. Could the galaxy be closer than it appears, not at high redshift at all, but at some intermediate distance where such a mass would be unremarkable? The photometry does not support it. The galaxy's colors are consistent with very high redshift. It really does appear to be where it appears to be. He checks for contamination. Could the photometry be affected by a nearby bright object, a nearby star, some instrumental artifact? He checks carefully. There is no obvious contamination. He sits with the number for a long time. Then, he calls his collaborators. What he tells them, in a quote he would later give to a journalist, is this: "We just kind of looked at each other and said, is this real?" The paper he and his team would publish in Nature in February of 2023 would describe a population of red candidate massive galaxies at extreme redshifts. 6 of them highlighted as the most striking examples, with stellar mass estimates that, if correct, were deeply in tension with the standard model of galaxy formation. One headline writer would later summarize the situation with 3 words that would travel around the world: "The Big Bang is broken." It was not. But what was happening was something genuinely strange. And the story of what JWST had actually found, what it really meant, how it was eventually partly resolved, and what remains unexplained, is more interesting than either the alarm or the dismissal. The galaxies were too big, too early, too structured, too numerous. There should not have been enough time after the Big Bang for them to exist. The standard model of galaxy formation, built over decades, calibrated against observations from earlier telescopes, said the early universe should contain only small, dim, primitive protogalactic structures. What JWST found was something else. And the question of what to do about that, how deep the revision needs to go, what assumptions need to change, is still being actively argued by the people who know this subject best. This video is about what the James Webb Space Telescope found in the early universe. JWST launched on Christmas Day of 2021. It is the most complex and most expensive space telescope ever built. A collaborative project between NASA, the European Space Agency, and the Canadian Space Agency, with development costs of approximately $10 billion. Its primary mirror is 6.5 meters across, made of 18 gold-coated beryllium hexagons. It is optimized for infrared light, which allows it to see through the dust clouds that block visible light in star-forming regions, and, crucially, to detect the light from the most distant galaxies in the universe, whose light has been stretched by cosmic expansion from visible and ultraviolet wavelengths into the infrared during its multi-billion-year journey to us. It was designed, in part, to look further back in time than any previous telescope and confirm what the standard model of cosmology predicted the early universe should look like. Within its first year of science operations, it found galaxies in the very early universe that were brighter, more numerous, and apparently more massive than any standard model of galaxy formation had predicted. The discovery sent a shockwave through the cosmological community. Headlines around the world proclaimed the Big Bang theory was broken, overturned, in crisis. Scientists argued about whether the measurements were real, what could explain them, and what the implications were for half a century of cosmological work. By 2024 and 2025, the picture had clarified, but not in the way the headlines suggested. The Big Bang itself remains on solid ground. Among the most thoroughly tested theories in all of science, it is not threatened by what JWST found. What is under genuine, active, documented scientific pressure is something more specific and more interesting. Our models of what happened after the Big Bang, of how the first galaxies formed and grew, of how efficiently the earliest stars assembled themselves out of the chaos of the young universe, were significantly more wrong than anyone had expected. And JWST, looking at the early universe directly for the first time, showed us exactly where those models were failing. By the end of this video, you will understand exactly what JWST found. You will understand why it was so unexpected. You will understand what the current best explanations are, including the discovery of an entirely new class of cosmic object that nobody had predicted. And you will understand what the discovery means, not for the Big Bang, which remains intact, but for our understanding of how the universe built its first structures in the critical first billion years. So, what exactly did JWST find in the early universe? Why were those galaxies too massive, too structured, and too numerous to fit the predictions of the model that thousands of cosmologists spent decades building? What are the little red dots? A new category of cosmic object that JWST discovered, that nobody had predicted, that turned out to be something stranger than anyone initially thought. And how do they change the picture? And if our models of galaxy formation were this wrong about the early universe, what else might we be wrong about? This is not a video about the Big Bang being wrong. Let me be direct about this, because the framing in a lot of popular coverage of this topic has been deeply misleading. The Big Bang theory, the expansion of the universe from an extraordinarily hot, dense state about 13.8 billion years ago, is not broken. The evidence for it is overwhelming, consistent, and has passed every observational test put to it for over half a century. The cosmic microwave background, the abundance of light elements produced in the first minutes of the universe, the expansion of space, confirmed in galaxies across billions of light years, the large-scale structure of the cosmic web, none of these are in question. What is under pressure is something more specific. The astrophysical models that describe how galaxies formed in the early universe, the assumptions that were built into simulations about how fast stars could form, how quickly dark matter halos could accumulate, what the first structures in the cosmos looked like on human observable scales. Those assumptions are being tested for the first time by JWST, and some of them are failing. This is not a minor academic footnote. The galaxy formation models are where most of our specific predictions about the early universe come from. Getting them wrong matters. Understanding how they are wrong, and what the correct picture actually is one of the most important open problems in modern cosmology. Stay with me. Quick pause. If you're enjoying this kind of slow, careful storytelling, hit subscribe. Galaxy Pulse goes deep on stories others rush through. Now, back to the early universe. To understand why JWST early galaxy discoveries were so surprising, we need to understand what we expected to find. The Standard Model of Cosmology makes specific, detailed predictions about what the early universe should look like. These predictions were built over decades of observation, theory, and computer simulation. They were the most successful set of cosmological predictions ever assembled, confirmed by satellite, ground telescope, and mathematical analysis across every scale we had previously been able to probe. And JWST was designed, in part, to test them at the frontier, to look further back in time than any previous telescope, and to see the early universe not as a statistical inference, but as a direct image. What it found, instead, sent the field into its most intense internal debate in decades. To understand why, we have to start with what the Standard Model actually says. The universe began approximately 13.8 billion years ago in a state of extraordinary heat and density. In the first fraction of a second, it was so hot that matter as we know it could not exist, only a seething plasma of fundamental particles. In the first 3 minutes, protons and neutrons fused together to form the nuclei of the lightest elements, hydrogen, helium, a trace of lithium. In the first 380,000 years, the universe cooled enough for electrons to combine with those nuclei and form neutral atoms. At that moment, the universe became transparent. The light released at that moment, the cosmic microwave background, has been traveling through space ever since, and we can still detect it today. After that, the universe entered what astronomers call the cosmic dark ages. There were no stars, there were no galaxies, there was no light in any wavelength we can observe today. Just a slowly cooling, slowly expanding universe of neutral hydrogen gas and dark matter, the latter unseen but gravitationally dominant. For tens of millions of years, nothing shone. But the dark ages were not static. Tiny fluctuations in density, quantum fluctuations from the earliest moments of the universe, imprinted on the structure of the cosmic microwave background, were slowly amplifying under gravity. Regions very slightly denser than average pulled in surrounding matter. Dark matter, which does not interact electromagnetically and so does not radiate energy away, clumped first. It formed dark matter halos, gravitational wells into which normal matter, the hydrogen gas, could eventually fall. That falling was the beginning of galaxies. As hydrogen gas fell into dark matter halos, it compressed, heated, and eventually crossed the threshold needed to ignite nuclear fusion. Stars lit up for the first time. Their ultraviolet light began ionizing the surrounding neutral hydrogen, the process called reionization. gradually clearing the cosmic fog that had persisted since the Dark Ages. By about 1 billion years after the Big Bang, reionization was largely complete. The universe had become transparent again, and the first primitive galaxies were forming, small and irregular, growing through mergers with each other and through continued accretion of gas from their surroundings. This entire story, the Dark Ages, the first stars, the reionization epoch, the assembly of the first galaxies, is the domain that JWST was built to observe directly. The standard model that describes this process, lambda CDM, stands for lambda dark energy, which drives the universe's accelerating expansion, plus cold dark matter made of slow-moving particles that clumps hierarchically, forming small halos first and larger ones later through mergers. Lambda CDM has passed extraordinary tests at large scales, the distribution of galaxies across billions of light-years, the acoustic peaks in the cosmic microwave background, the way galaxy clusters grow over time. On all of these scales, lambda CDM is extraordinarily precise. Where lambda CDM is less precise is in its predictions about the internal physics of galaxies, the messy details of how gas falls in, how stars form, how stellar explosions and radiation push gas back out, how black holes grow and affect their surroundings. These processes, collectively called baryonic physics or galaxy formation physics, are modeled in computer simulations, but with parameters that have to be calibrated against observations because the underlying physics is too complex to calculate from first principles. Pause here for a moment, because this distinction is going to matter enormously. JWST is a telescope with a primary mirror 6.5 meters across, optimized for infrared wavelengths from about 0.6 to 28 microns. The Hubble Space Telescope, by comparison, has a 2.4-meter mirror and can detect infrared light only out to about 1.6 microns. JWST collects more than 6 times as much light as Hubble, and, in the infrared, it can see wavelengths that Hubble cannot reach at all. Wavelengths that are essential for detecting the most distant galaxies, whose visible and ultraviolet light has been stretched by cosmic expansion into the infrared during its multi-billion-year journey to us. JWST was not just a bigger Hubble. It was a fundamentally different instrument, capable of seeing things that had been completely invisible to all previous telescopes. And, when it looked at the early universe, it saw something that the models built on lambda CDM had not predicted. Under lambda CDM, combined with our best models of galaxy formation, here is what we expected JWST to find in the very early universe. Small galaxies. The hierarchical nature of structure formation means that small halos form first, and larger structures assemble later through mergers. In the first billion years, the halos available to host galaxies should be small, so the galaxies should be small, dim galaxies. Small galaxies contain fewer stars. Fewer stars mean less total light. So, the galaxies should be dim, irregular, primitive galaxies. The organized structures we see in mature galaxies today, spiral arms, elliptical profiles, rotating disks, take billions of years to develop through the accumulation of mass and angular momentum. In the first billion years, galaxies should be messy, irregular, still assembling, and few in number, particularly at the highest redshifts. The further back in time you look, the fewer galaxies should have assembled to sufficient mass to be detectable. This picture was not a rough sketch. It was the output of sophisticated simulations, calibrated against decades of observations with Hubble and ground-based telescopes, encoding the best understanding of how galaxies form that decades of astrophysics had produced. What JWST found in its first year of science observations diverged from this picture on almost every dimension. The galaxies were brighter than expected, dramatically, more numerous at high redshifts than models predicted. Some of them appeared, in initial estimates, to have stellar masses comparable to the Milky Way, observed at a time when the universe was only 5 to 7% of its current age. Some had already stopped forming stars entirely, a state called quiescence, at epochs when models said they should be in the full flower of star formation, and at least some appeared to have organized, structured morphologies, inconsistent with the messy, irregular appearance expected of such young systems. The gap between prediction and observation was not subtle. Rachel Somerville, a galaxy formation expert at the Flatiron Institute, put it plainly in a published comment. As more data came in, it became clear that the abundance of early bright galaxies was higher than theorists had predicted. It was an incredibly exciting time. The standard model was not destroyed, but it was confronted with data it had not been designed to accommodate. The story of the first major anomaly begins on the night of July 12, 2022, when NASA released the first public science images from JWST. One of those images was the SMACS 0723 Deep Field, a dense patch of sky containing thousands of galaxies, including some of the faintest, most distant objects ever imaged. The public reaction was immediate and intense. The image was stunning, the galaxies were extraordinary, the detail was beyond anything Hubble had produced in comparable exposures. For researchers, the reaction was similar, but with an additional layer. The galaxies in the image were not behaving the way the models said they should. Ivo Labbé and his collaborators were among the first to quantify what was wrong. They selected a subset of objects from the early JWST data that appeared, from their colors, to be at very high redshift, corresponding to a period when the universe was between roughly 500 and 750 million years old. Then, they estimated the stellar masses of these objects using standard photometric techniques, measuring the brightness of each object across multiple infrared wavelength bands and comparing those brightness measurements to models of how stellar populations of different ages and compositions should appear. The masses that came back were alarming. A handful of galaxies with stellar masses that, according to the estimates, placed them in the same league as the most massive galaxies in the modern universe, despite being observed at an epoch when the universe had barely had time to form any galaxies at all. One of the candidates appeared to have a stellar mass approaching 10 to the 11th solar masses, 100 billion times the mass of the Sun, at extreme redshift. Labbé, in his own words, asked himself and his team, "Is this real?" The paper that resulted, published in Nature in February of 2023, under the title A Population of Red Candidate Massive Galaxies 600 m after the Big Bang, was careful. The authors described their candidates as massive galaxy candidates, acknowledged the uncertainties in photometric mass estimation, and noted that spectroscopic confirmation would be needed to verify the results. But they also calculated the implications if the measurements were correct. To contain as much stellar mass as some of these galaxies appeared to have, at their claimed redshifts, the universe would have had to convert available normal matter into stars with an efficiency approaching, in some cases exceeding, 100%. Standard stellar physics says this is impossible. Stellar feedback, the energy released by massive stars in the form of radiation, stellar winds, and supernova explosions, expels gas from galaxies before it can all be converted into stars. A 100% conversion efficiency violates our understanding of how stars form. This was the analysis that set off the alarm. Not just the masses themselves, but the implication that the models could not accommodate such masses, even in principle, without invoking physics that violated known constraints. Mike Boylan-Colchin, a cosmologist at the University of Texas at Austin, published a companion analysis in Nature Astronomy showing that if the Labbé galaxies were real and at their claimed redshifts, they would require either baryon conversion efficiencies approaching 100% or dark matter halo masses that exceeded the predictions of lambda CDM itself. The community's reaction was divided, as it always is when dramatic claims emerge from early data with a new instrument. Some researchers were alarmed, others were skeptical. Nearly everyone agreed that more data, and specifically spectroscopic confirmation of the redshifts and masses, was urgently needed. What came next would complicate the picture considerably. Before we go further, let us make sure the science here is clear, because the rest of this story depends on understanding a few things, and they are not difficult things. They have just been obscured in most popular coverage by a combination of jargon and overclaiming. Think of it this way. Imagine you are an urban planner and you have been given a precise budget for how many bricks will be available to build a city in its first 10 years of existence. Your calculations are solid. You know how fast bricks can be manufactured given the available raw materials. You know how long it takes to lay them. You know how much of the supply gets wasted in the process. Based on all of this, you have predicted the maximum possible height of any building in the city after 10 years. Your prediction is detailed, tested, and has worked well for every city you have modeled before. Then you look at satellite images of the new city, and there are 40-story skyscrapers. To have built those buildings in 10 years, using all available bricks, the construction crews would have had to achieve nearly perfect efficiency, no waste, no mistakes, every brick in exactly the right place, the entire budget devoted to these single structures. And there are several of them. The only way the math works is if something about the brick supply, or the construction physics, or the city planning assumptions, is fundamentally different from what you thought. That is, roughly, the situation with JWST early galaxies. There are 3 things you need to understand to follow what comes next. The first is stellar mass, and why it is the crucial measurement. Stellar mass, the total mass of all stars in a galaxy, is the single most fundamental property of a galaxy in the context of this story. It tells you how many bricks the city contains. You cannot determine stellar mass directly from a photograph. You have to infer it from the galaxy's brightness at multiple wavelengths, compared to models of how stars of different ages and compositions contribute to that brightness. This inference is indirect, and it carries uncertainty, but it is the best available tool for galaxies too distant to study in any other way. The second is the baryon conversion efficiency. The universe started with a known amount of normal matter, baryons, distributed across space in proportion to the dark matter halos that gathered it. The fraction of that available matter that gets converted into stars in any given galaxy is called the baryon conversion efficiency. Standard physics says it should be a few percent, maybe 10% at the extreme high end, because stellar feedback processes expel most of the gas before it can form stars. If the JWST galaxies require conversion efficiencies of 50 or 100%, something in our understanding of this process is wrong. The third is redshift, and what it tells us. Redshift is the stretching of light to longer wavelengths as it travels through an expanding universe. The higher the redshift, the farther away and the further back in time the object. A galaxy at redshift 7 is seen as it was when the universe was about 750 million years old. At redshift 10, about 460 million years old. At redshift 13, about 320 million years old. When astronomers say a galaxy is at a high redshift, they mean it is ancient, seen as it existed in the first billion years of cosmic time. Photometric redshifts, estimated from the galaxy's colors, are less reliable than spectroscopic redshifts, measured from specific lines in the galaxy's spectrum. Some of the early JWST anomalies dissolved when spectroscopic follow-up showed the objects were at lower redshifts than initially estimated. Others were confirmed, and the anomalies stood. So here is where the stakes start to rise. If even a subset of the early JWST galaxy candidates are real, if even a fraction of the excess brightness and apparent mass at high redshifts holds up to scrutiny, then something about our models of galaxy formation in the early universe was significantly wrong. Not the Big Bang, not the expansion of the universe, not the age of the cosmos, or the formation of the cosmic microwave background, or the nucleosynthesis of hydrogen and helium in the first minutes. None of these are in question. What is in question is the specific set of astrophysical assumptions encoded in galaxy formation simulations. The models that tell us how dark matter halos grow, how gas cools and falls in, how efficiently it forms stars, how supernova and radiation push it back out. These models had been calibrated primarily against observations of the universe at moderate redshifts, roughly 1 to 3 billion years after the Big Bang. They had never been directly tested against observations of the first billion years, because no previous telescope had been capable of imaging that epoch in detail. JWST was the first telescope capable of testing these models where they had never been tested before, and the test was revealing something uncomfortable. The stakes extend beyond the purely academic. Galaxy formation models are the foundation on which we build our understanding of how the universe's structure evolved, how the first galaxies gave rise to the ones we see today, how the properties of galaxies relate to the dark matter halos in which they live, how the universe transitioned from the homogeneous plasma of the Big Bang to the rich, complex web of cosmic structure we observe around us. If those models are significantly wrong about the early universe, they may also be wrong about processes that connect the early universe to the present day. This was not a minor data point requiring a small correction. This was a first look at a previously inaccessible epoch of the universe, and the first look was showing something unexpected at almost every turn. If the massive early galaxy problem had been the only surprise JWST produced in its first 2 years, the story would have been about updating galaxy formation models. A significant revision, but a bounded one. But JWST data produced a second discovery, entirely separate from the massive galaxy problem, entirely unexpected, and in some ways stranger, that would change the picture in ways nobody anticipated. In 2023 and 2024, as more JWST deep field data accumulated, astronomers began noticing a new kind of object. Compact, very red. Too bright to be a normal galaxy at those redshifts. Too faint for a known quasar. Too red for any standard model of galaxy or stellar population. Objects that did not fit into any existing category in the cosmic zoo. They called them little red dots, and what they turned out to be surprised almost everyone. In 2023 and 2024, as the JWST deep field surveys accumulated enough data to begin statistical analysis, a pattern emerged that had not been anticipated by any pre-launch prediction. Scattered across the deep field images were objects that did not fit. They appeared compact, essentially point sources in the JWST images, lacking the extended, resolved structure of a galaxy. They were red, very red, in a color combination that is unusual for any known class of astronomical object at high redshift. They were bright, bright enough to be detected easily, but in a way that was inconsistent with their apparent size, and they were numerous, far more numerous than any pre-existing model had suggested should exist. Researchers began calling them little red dots, a casual name that stuck, partly because the objects looked like exactly that in the infrared imaging data, and partly because no formal classification existed yet. The initial interpretations were varied, and the debates were intense. The first serious proposal was that little red dots were compact, dusty, star-forming galaxies, systems undergoing extremely rapid star formation that was heavily obscured by dust. The dust would absorb ultraviolet and visible light from young stars and re-emit it as infrared radiation, reddening the galaxy's appearance dramatically. Some examples of such galaxies existed from pre-JWST observations, but not in anywhere near the numbers that JWST was finding little red dots. The second proposal was that they were compact quiescent galaxies, galaxies that had already stopped forming stars at very early epochs. Their stellar populations evolved, and therefore red, their small size reflecting the compact morphology of early passive galaxies. This was itself a puzzle, since such early quenching was not expected in standard models, but it was at least a known category of object extended to extreme redshifts. Then came the paper that settled the question for most researchers. In 2024, Jenny Green at Princeton and a large collaboration published a systematic analysis of little red dots across multiple JWST deep field programs. They identified over 700 of these objects. They performed detailed spectroscopic analysis of a significant subset, and the picture that emerged was striking. The little red dots are not primarily galaxies. They are supermassive black holes, actively accreting black holes, in the early universe, surrounded by dense gas and dust that scatters, absorbs, and re-emits their light in the unusual color patterns JWST had detected. They belong to a class of objects called active galactic nuclei, or AN. But they are AGN with properties unlike anything in the pre-JWST catalog. Their host galaxies, if they have detectable galaxy components at all, are often small and faint. The dominant light comes from the black hole itself, not from stars. This discovery had an immediate implication for the early massive galaxy problem. Some of the most dramatic massive galaxy candidates from the early JWST data, the ones with the most alarming stellar mass estimates, the ones most in tension with the standard model, turned out, when looked at carefully, to be little red dots. Objects dominated by black hole light, not stellar light. Their apparent stellar masses had been drastically overestimated because the analysis tools used to extract stellar mass from galaxy photometry were not designed to handle the contribution of a bright, embedded black hole. When the little red dots were identified and removed from the massive galaxy samples, when the galaxy population was cleaned of these contaminants, the tension with the standard model dropped substantially. Not to zero, but substantially. A significant fraction of what had appeared to be the signature of early massive galaxy formation was, in reality, the signature of early supermassive black hole formation. A different problem. No less interesting, but not the same problem. This is, in itself, a genuinely important discovery. The little red dots represent a population of supermassive black holes in the early universe that nobody had predicted. They are more numerous than expected. They appear to be growing more rapidly than standard models allow. The question of how supermassive black holes got as big as they are, as early as they did, is now one of the most active research questions in observational cosmology. A question that JWST opened by discovering little red dots while looking for something else entirely. The lesson here is important and worth dwelling on. The little red dots were not simply an error. They were not merely a measurement artifact that went away when the data got better. They are real cosmic objects, present in the early universe in abundance, doing something we did not predict and do not yet fully understand. JWST, in the process of finding something surprising, found something even more surprising, and the story was not over. Because, When you removed the little red dots from the sample, you were left with genuine early galaxies, real star-forming systems at high redshift, and some of them were still more numerous, still more massive, still more structured than the standard model had predicted. The problem shrank, it did not disappear. In August of 2024, NASA published a study with a headline that was notable for its unusual directness. Webb finds early galaxies weren't too big for their britches after all. The paper, by Catherine Chworowski, Stephen Finkelstein, Michael Boylan-Colchin, and colleagues at the University of Texas at Austin, was one of the most comprehensive analyses of the early massive galaxy problem yet published. It appeared in the Astronomical Journal, based on data from the JWST Cosmic Evolution Early Release Science Survey, SEERS, using the most careful mass estimation methods available, methods that accounted for the AGN contribution, for calibration improvements in the JWST instruments, for the biases introduced by using photometric rather than spectroscopic mass estimates. The team found that many of the most alarming original claims were significantly overstated. The galaxies, in the new analysis, were still massive, but they were no longer catastrophically in tension with the standard model. Some of the most extreme mass estimates had been revised downward by factors of several. The Baryan conversion efficiencies required to explain the genuine galaxy sample, once the little red dots were removed, no longer approached 100%. Chworowski's own framing was careful. We are still seeing more galaxies than predicted, although none of them are so massive that they break the universe. That phrasing matters, not because the science is dramatic, but because it is honest. Stephen Finkelstein, the SEERS principal investigator and a co-author on the paper, put the bottom line plainly. The bottom line is there is no crisis in terms of the standard model of cosmology. The headline was, in a sense, a corrective to 2 years of alarm. The Big Bang was never broken. The galaxy formation models had some explaining to do, but the gap between theory and data was not as vast as the early reports had suggested. But the paper was also careful to note something that got less attention. Even after all the corrections, after the calibrations, after the little red dot removal, after the improved mass estimation, there were still more massive early galaxies than the standard model cleanly predicted. The number density of galaxies at redshifts between 4 and 8, at stellar masses above certain thresholds, remained elevated relative to model expectations. The tension was reduced. It was not eliminated. And simultaneously, JWST was producing other surprises that were separate from the mass question entirely. In March of 2025, an international team led by Weiken Wang and colleagues, including Themia Nanayakara at Swinburne University of Technology, published in Nature Astronomy the discovery of a galaxy they named the Big Wheel. The Big Wheel is a massive spiral disk galaxy with an optical radius of around 10 kiloparsecs, at least 3 times larger than current cosmological simulations predict for galaxies of its epoch. It is at redshift 3.245, observed at a time when the universe was only about 2 billion years old. It is comparable in size to today's most massive disk galaxies. This was deeply puzzling. The development of organized spiral structure in a galaxy requires enormous amounts of time. Spiral arms form through differential rotation, through the accumulation of stars and gas into a rotating disk, through the stabilization of that disk against disruption by the chaotic mergers that are common in the early universe. These processes, in standard models, take billions of years. The Big Wheel appeared to have completed them in about 2 billion. Nanayakara's framing. This galaxy not only challenges our existing models of early formation, but also hints that dense, gas-rich environments may be the cradle for the universe's earliest giants. The galaxy lives in an unusually crowded region of space, about 10 times denser than typical areas of the universe. That dense environment may have enabled rapid growth through frequent but gentle galaxy interactions. Either the galaxy formed and organized with extraordinary speed, efficiency again, but this time of a different kind, or something about our understanding of how galaxies assemble their structure in dense environments is incomplete. Then, in May of 2026, came another surprise. A team, led by Ben Forrest at UC Davis, working with the MAGAS 3NE survey, Massive Ancient Galaxies at High Redshift, published in Nature Astronomy. The discovery of a galaxy designated XMMVID 1-275. This galaxy is massive, containing several times the stellar mass of the Milky Way. It has already stopped forming stars, it is quiescent, dead, its star formation shut down, and it shows essentially no organized rotation. It was observed at redshift 3.449, when the universe was less than 2 billion years old. The no rotation finding was the most puzzling part. In the standard picture of galaxy formation, galaxies inherit angular momentum from the mergers and accretion events that build them. Young galaxies spin, they rotate. The gradual loss of rotation, the transition to the slow, random orbital motion seen in old elliptical galaxies, is the product of many violent interactions over billions of years. It is not supposed to happen this fast. Yet, XMMVID 1-275 showed essentially no organized rotation. Less than 2 billion years into the universe's history, Forrest's own framing was careful. This one in particular did not show any evidence of rotation, which was surprising and very interesting. The team observed 3 massive galaxies of comparable age. One was clearly rotating. Another showed irregular motion. The third, XMMVID 1-275, showed dispersion-dominated kinematics, with stars moving in random directions instead of organized circulation. The team's leading hypothesis is not slow accumulation through many mergers, but rather a single, high-energy collision between 2 galaxies moving in opposite directions, which would have canceled angular momentum in one event and may have expelled the gas that fuels star formation. Either way, the implication is plain. This galaxy had gone through processes that should take billions of years: mass assembly, quenching of star formation, loss of organized rotation, in a fraction of that time. Something about the timeline of galaxy evolution in the early universe is not what the standard picture predicted. As Rachel Somerville, one of the field's leading galaxy formation theorists, said in a published comment, "In retrospect, it's perhaps not surprising that these things were different in the early universe, but the assumption that they were the same had been hard-coded into the models. With JWST data, that is now changing. So the problem is real, reduced from its initial alarming dimensions, but real. The early universe contains more massive galaxies, more quickly quenched galaxies, and more structurally developed galaxies than our models predicted." What can explain this? 3 candidate explanations currently lead the scientific discussion. They are not mutually exclusive. All 3 may be partly correct, but they have different implications for how deep the revision to our models needs to go. The first explanation is that early universe star formation was simply more efficient than our models assumed. In the modern universe, star formation is an extraordinarily wasteful process. Of all the gas available in a typical dark matter halo, only a few % ever gets converted into stars. The rest is ejected by stellar feedback. The energy released by massive stars in the form of radiation, stellar winds, and the shock waves from supernova explosions. This feedback is what prevents the baryon conversion efficiency from approaching 100%. But feedback depends on the properties of the stars doing the feeding back. In the very early universe, the gas available for star formation was chemically different. It was almost purely hydrogen and helium, with essentially none of the heavier elements that enrich later generation gas. Stars formed from this primitive gas were probably more massive, hotter, and shorter-lived than stars formed from modern metal-enriched gas. And massive, hot stars have different feedback properties than smaller, cooler ones. If the specific feedback physics in the very early universe allowed a higher fraction of available gas to be converted into stars before that gas was expelled. Maybe 10% instead of a few percent, maybe 20%. Many of the observed properties of early JWST galaxies become more plausible without requiring any revision to the underlying cosmological model. The weakness of this explanation is that it requires early universe star formation physics to be substantially different from what we have modeled. We do not yet have a complete theoretical account of why and how that difference would arise. The second explanation involves the growth of dark matter halos. The stellar mass of a galaxy is, ultimately, limited by the mass of the dark matter halo it inhabits. Dark matter sets the gravitational well. The galaxy fills it. If dark matter halos in the early universe grew faster than lambda-CDM cleanly predicts, if the growth of structure was more rapid in the first billion years, then the halos available to host galaxies would be more massive earlier, and the galaxies within them could consequently reach higher stellar masses sooner. This explanation, taken to its logical conclusion, would require modifications to lambda-CDM itself, specifically, to the predictions it makes about how dark matter structure grows in the early universe. That is a significant step. Lambda-CDM's predictions about structure growth have been tested and confirmed over a wide range of scales. Modifying them to resolve the early galaxy tension would require those modifications to remain consistent with all existing observational constraints. This is technically possible, but it is a strong requirement. The third explanation is the most radical. Perhaps the excess of bright early galaxies, even the reduced excess that survives after calibration corrections, little red dot removal, and improved mass estimation, is large enough, robust enough, and consistent enough across independent observations that it signals a genuine inadequacy in the cosmological model itself. Lambda-CDM is not the only tension in modern cosmology. There is the Hubble tension, a disagreement between early universe and late universe measurements of the expansion rate of the cosmos, that has persisted for over a decade and has, if anything, sharpened as the measurements have become more precise. There is the S8 tension, a similar disagreement about the amplitude of matter clustering. Some theorists have proposed modifications to the early universe, specifically, a period of enhanced dark energy activity called early dark energy, that might simultaneously alleviate several of these tensions. If early dark energy were real, it would have accelerated the growth of structure in the universe's first million years, producing more massive dark matter halos earlier, which could explain the early massive galaxy problem as a consequence of a modified cosmological model rather than modified galaxy physics. The weakness of this explanation is that it requires a change to lambda-CDM's core architecture. Changes of that magnitude require extraordinary evidence, and while the multiple tensions in lambda-CDM are suggestive, they are not yet individually or collectively strong enough to demand a modification to the underlying model. The honest scientific position is that all three explanations may be partly correct, and that resolving which one, or which combination, is right will require more data, more careful analysis, and probably more discoveries from JWST and the telescopes that will follow it. There are three ways to interpret what the full body of JWST early universe data tells us about our cosmological framework. They sit on a ladder, from the most conservative to the most bold. Each one is held by a real segment of the cosmological community. Each one has genuine supporting evidence, and none of them has yet been definitively confirmed or ruled out. The conservative interpretation is that the problem is primarily astrophysical and is largely resolved. In this view, the initial alarm over the JWST early massive galaxies was a product of early instrument calibration uncertainties, the misidentification of little red dots as galaxies, and the limitations of photometric mass estimation. The August 2024 Jaworski paper shows that when these issues are properly addressed, the tension with lambda CDM drops to a manageable level, something that can be accommodated by allowing somewhat higher star formation efficiency in the early universe, without requiring any changes to the cosmological model. The supporting evidence is strong. The calibration improvements were real. The little red dot contamination was real and significant. The revised mass estimates, while still showing some excess, do not require implausible baryon conversion efficiencies. Stephen Finkelstein, the SEER's principal investigator, has been explicit on this point. The bottom line is there is no crisis in terms of the standard model of cosmology. The weakness is the ongoing anomalies. The non-rotating massive quiescent galaxy, the big wheel, the persistently elevated number density of massive early galaxies even after all corrections. If these are also resolved by astrophysical adjustments, the conservative view wins. If they are not, something more is needed. This remains the majority view in the cosmological community, though it is held with more qualification than it was before JWST launched. The moderate interpretation is that galaxy formation models require substantial revision, even if the cosmological model does not. In this view, the JWST data is telling us something genuine and important about how galaxies form in the early universe. The star formation physics in the first billion years was qualitatively different from what our models assumed. Feedback was less efficient. Halos were more conducive to rapid mass assembly. The timescales over which galaxies can become quiescent, organized, and mature were shorter than the simulations predicted. These revisions do not require changing lambda CDM. They require changing the baryonic physics built on top of it. The detailed models of how gas turns into stars, how stars influence their surroundings, how galaxies interact and merge. This is a significant undertaking, but it is bounded. It does not require new cosmology. This view is supported by the convergence of multiple independent anomalies in JWST data pointing in the same direction: early massive galaxies, early quiescent galaxies, early spiral structure, all suggesting that the processes of galaxy evolution operate on faster timescales than standard models predict. The weakness is that revising galaxy formation models is not yet a specific prescription. We know something needs to change. We do not yet know exactly what. The bold interpretation is that lambda CDM itself needs modification. In this view, the early galaxy problem is one of several tensions in the standard model. Taken together, with the Hubble tension, the S8 tension, and any remaining JWST excess after astrophysical corrections, these tensions may indicate that the core cosmological framework needs to be updated, not abandoned, but extended or modified in ways that preserve its successes while accommodating the new observations. The most discussed modification in this context is early dark energy, a transient period of accelerated expansion in the early universe that would have altered the growth of structure on scales relevant to galaxy formation. Some analyses suggest that early dark energy could simultaneously alleviate the Hubble tension and the early galaxy problem, at the cost of changing the cosmological model in ways that would need to be tested against other observations. This view is a minority position, but it is taken seriously by serious scientists. Before we leave the theoretical landscape, there is something worth saying about what this entire story means. We built a picture of the early universe without being able to see it directly. We used mathematics, simulation, and the indirect traces of ancient structure preserved in the cosmic microwave background and the statistical properties of galaxies in the relatively nearby universe. We built something extraordinarily successful, a model that correctly predicted the large-scale structure of the cosmos, the geometry of spacetime on cosmic scales, the acoustic oscillations in the distribution of matter across billions of light years. And then we built an instrument that could actually look. For the first time in the history of astronomy, the early universe was not a theoretical inference. It was an image, and the image showed things that the model had not quite captured, not enough to overthrow the model, but enough to demand that we update it, question it, test it more carefully than before. That is not a failure. That is how science is supposed to work. For most of human history, the universe was a still photograph. We studied it by capturing its faint light and extracting every possible piece of information from that light, across multiple wavelengths and many decades of accumulated data. With JWST, for the first time, we are getting something closer to a movie of the universe's history, not just snapshots of the present, but actual images of the past, going back further and further toward the moment everything began. And the movie shows us things we were not expecting. After everything we have seen, the galaxies that initially looked impossible, the little red dots, the revised mass estimates, the persistent anomalies, the three competing interpretations. The question is no longer whether JWST has found something unexpected. It has. The question is how deep the revision needs to go, and what the unexpected findings are actually telling us about the physics of the early universe. And here is where the story takes a turn that most coverage has never gotten to. Here is the strange thing about how JWST early galaxy discoveries have been covered. The story has gone through a predictable cycle, one that has played out with other scientific controversies before and will play out again. The dramatic claim gets enormous coverage. The careful revision gets buried. The public is left with the impression of either permanent crisis or permanent resolution, depending on which wave of coverage they happen to encounter. Let me give you specific examples of what the headlines missed. The first is the calibration story. JWST instruments were still being calibrated during the first months of science operations. The flux calibration, the conversion between raw detector counts and physical brightness units, was not yet at its final accuracy. Some of the most alarming early mass estimates were based on data where the calibration was still being refined. As the calibration improved through 2022 and 2023, some of the most extreme mass estimates changed, not dramatically, but measurably, in the direction of reducing the tension. This is completely normal for a new space telescope. Hubble's instruments were also calibrated on orbit, and the early Hubble data required similar revisions. But the popular coverage did not track the calibration improvements. Articles written in August of 2022, based on early data, were still being cited in 2025 as if they represented the current scientific consensus. The snapshot of maximum alarm became the permanent public narrative. The second thing the headlines missed was the magnitude of the little red dot story. When the little red dot population was identified, when it became clear that a significant fraction of the most dramatic massive galaxy candidates were actually AGN, not galaxies, this was reported as a resolution or a debunking. Some articles framed it as proof that the whole JWST galaxy problem was a measurement error. That framing missed two important things. First, even with the little red dots removed, a real tension remained. Second, and this is the part that got almost no coverage, the little red dots are themselves a major scientific discovery. A population of hundreds of rapidly growing supermassive black holes in the early universe, not predicted by any model, raising its own set of profound questions about how black holes grew so large so quickly. The little red dots are not a footnote to the JWST galaxy story, they are a chapter in their own right. The third thing the headlines missed was the nuance of the Jaworski paper. Webb finds early galaxies weren't too big for their britches after all, was a genuine corrective. It was important science, but the popular coverage of it made it sound like the case was closed, the Big Bang was fine, nothing to see here. The actual paper said something more careful. It said that with improved methods, the tension was significantly reduced. It did not say the tension was zero. It explicitly noted, "We are still seeing more galaxies than predicted, although none of them are so massive that they break the universe." The difference between a significantly reduced tension and no tension is the difference between the problem is smaller than we thought and there is no problem. Popular coverage consistently conflated these two things. The fourth thing the headlines missed were the new anomalies. While the public conversation focused on whether the massive galaxy problem was real or a measurement error, JWST was quietly producing other findings that received much less attention. The non-rotating massive quiescent galaxy, XMMVID 1-275, published in May 2026. The Big Wheel Spiral Galaxy, published in March 2025. Both of these represent genuine puzzles in galaxy formation theory that are independent of the mass estimation debate. Both received far less coverage than the original Labbé paper or the Jaworski revision. The scientific story of JWST and the early universe is richer, more complicated, and more interesting than any single wave of popular coverage has captured. The field is not in crisis. It is in the most productive kind of scientific ferment, where new data is forcing genuine questions about models that have been comfortable for too long, and where the answers, when they come, will leave us with a better understanding of how the universe actually works. In the months and years since the Jaworski paper, the data pipeline from JWST has continued to produce results that are reshaping our understanding of the early universe in ways that go beyond the massive galaxy problem. The first major development is the JADES program, the JWST Advanced Deep Extragalactic Survey. JADES is the deepest and most comprehensive galaxy survey that JWST has yet conducted, spanning multiple pointings across two primary fields. JADES has now accumulated enough data to begin building statistically robust samples of early universe galaxies across a wide range of redshifts and luminosities. The results being published from JADES are transforming the statistical picture of the early universe. For the first time, astronomers have enough confirmed early universe galaxies, spectroscopically verified, with reliable redshifts and reasonable mass estimates, to measure the galaxy luminosity function at redshifts above 10 with real precision. What JADES is showing is that at the very highest redshifts, approaching the first few 100 million years after the Big Bang, the bright end of the luminosity function is elevated relative to standard model predictions, not catastrophically, but measurably, and in a way that is consistent across independent survey programs. This is important. It suggests that the JWST early galaxy excess is not a statistical fluke, not a measurement artifact, not something that will go away with better calibration. It is a real feature of the early galaxy population that the models need to accommodate. The second development is in the spectroscopic characterization of little red dots. As JWST spectroscopic programs have accumulated more data on little red dots, the picture of what these objects are has become more detailed and more complex. Most little red dots show spectral signatures consistent with actively accreting black holes. But some show signs of host galaxy emission as well. There may be a population of little red dots that are genuinely transitional objects, systems in which the galaxy and the black hole are both growing rapidly, in a configuration we have not previously observed because we lacked the instruments to see it. The third development is the increasing evidence that early quenching is genuinely more common than expected. Multiple independent JWST programs have now confirmed the existence of massive quiescent galaxies at redshifts above 3. Galaxies that had assembled their stars and stopped forming new ones in the first 2 billion years of the universe. The number density of these objects is higher than any pre-JWST model had predicted. The combination of high stellar mass and early quenching is particularly challenging because quenching, the shutting off of star formation, is thought to require a specific set of physical conditions that take time to develop. How do you form hundreds of billions of solar masses of stars and then stop in less than 2 billion years? This question does not yet have a satisfying answer. The fourth development is the Hubble tension connection. JWST has weighed in on the Hubble tension, the disagreement between measurements of the universe's expansion rate made from the early universe using the cosmic microwave background and from the late universe using supernova and Cepheid variable stars. JWST has been used to precisely calibrate the Cepheid distance ladder that underlies the late universe measurement. The result, published in multiple papers, is that the Hubble tension is real. JWST Cepheid measurements confirm the late universe expansion rate with high precision, and it continues to disagree with the early universe value. This is a separate problem from the early galaxy issue, but both point toward the same uncomfortable possibility that something in our standard cosmological framework may need revision. The next decade of observational cosmology will be shaped by what JWST is doing right now. The first thing to understand is that the statistical samples are still growing. JWST has been in science operations for less than 4 years. Its expected mission life is at least 20 years, with fuel and technical longevity suggesting it could operate for considerably longer. Many of the debates that are currently unsettled will be settled by sheer statistical power. The second thing to understand is that complementary instruments are coming. The Nancy Grace Roman Space Telescope will survey enormous areas of the sky in the infrared. Where JWST goes deep, Roman will go wide. The combination of Roman's wide area surveys and JWST deep targeted follow-up will produce a picture of early universe galaxy populations that is statistically far more robust than anything possible today. The extremely large telescope, under construction in the Atacama Desert in Chile, will be capable of taking spectra of the faintest JWST-discovered galaxies, objects currently accessible only to JWST photometric imaging. Together, JWST, Roman, and the ELT will transform our understanding of the early universe within the next decade. The third thing to understand is that galaxy formation theory is being actively updated. The JWST findings have already prompted revisions to the galaxy formation models used in major simulations. Codes like Illustris-TNG, Fire, and Eagle are being updated to accommodate the observational constraints that JWST has established. Some of these updated simulations are already producing galaxies that look more like what JWST observes. Not perfect agreement, but closer. The fourth thing to understand is the broader lesson for cosmology. The history of lambda CDM is the history of a model built from increasingly precise, indirect observations. each new generation of data revealing new details and occasionally new tensions. Each generation of data improved the model, and each generation occasionally introduced tensions that took years to resolve, sometimes through better data, sometimes through model revision, sometimes through new physics. JWST is the latest generation. Its findings are already improving the model. Whether they ultimately require new physics, whether the Hubble tension, the early galaxy excess, and the other tensions converge on a genuine inadequacy in lambda CDM, is the central open question of contemporary cosmology. The answer will come. It always has, and here is what makes all of this truly remarkable. JWST was built, in part, to test lambda CDM at the frontier, to look at the early universe directly for the first time and confirm what decades of theoretical work and indirect observation had led us to expect. Instead, it found something different, not so different that the entire framework collapsed, not so different that we are lost, without a model, without a roadmap, but different enough that the field is now engaged in the most intensive reanalysis of early universe galaxy formation theory in decades. It isn't the tension itself that is remarkable. Tensions between model and observation are not unusual in physics. The history of science is full of them. What is remarkable is what this particular tension reveals about how science works. For decades, we built a picture of the early universe without being able to see it. We constructed that picture from mathematical inference, from indirect observations, from the statistical properties of a universe we could study only in its middle and late periods. We built something extraordinary, a model that correctly predicted the geometry of spacetime on cosmic scales, the large-scale distribution of matter across the observable universe, the proportions of hydrogen and helium baked out in the first minutes of cosmic time. We were right about so much. And then, for the first time, we actually looked, and the early universe was doing something with its galaxies that our model had not quite captured. Let that sit for a moment. The most successful cosmological model in the history of science. A model that has passed tests at scales from the subatomic to the cosmic, turned out to have missed something about how the very first galaxies formed in the first billion years. The miss is not catastrophic. It is, in some ways, expected. We were extrapolating into territory we had never directly observed. The extrapolation was good. It was not perfect. And the imperfection is where the next generation of understanding will grow. Because here is what the JWST early galaxy story is really about. It is not about galaxies. It is not about the Big Bang. It is about the process of getting better, of building the best possible model from available evidence, of then developing the instruments to directly test that model where it had never been tested before, of finding the places where the model fails, and of following those failures, carefully, honestly, without overclaiming and without dismissing, into a more accurate picture of reality. That is not a crisis. That is the most important thing science can do. And the universe, it turns out, is still doing things we haven't figured out how to predict, which means we have more to learn, which means JWST was not the answer. It was the most powerful question ever built, but there is one more piece to this story. Because the early galaxy problem is not the only tension that JWST has weighed in on. There is another one, the Hubble tension, a disagreement about the expansion rate of the universe that has been growing for a decade, and that JWST has now confirmed rather than resolved. Some cosmologists consider the Hubble tension to be the single most serious challenge to the standard cosmological model currently known. Others think it will trace to systematic measurement errors that have not yet been identified. That is a story for next time. Tonight, we did not just learn about galaxies that shouldn't exist. We watched what happens when, for the first time in the history of our civilization, a telescope powerful enough to actually image the early universe, is pointed at it, and sees something the model didn't quite predict. We saw Ivo Labbé in the summer of 2022, staring at photometry numbers that did not fit, asking his collaborators whether what he was looking at was real. We watched the field erupt into debate, the alarm, the skepticism, the calibration questions, the months of follow-up and verification. We watched a new category of cosmic object emerge from the data, little red dots, hundreds of them, scattered through the deep fields, behaving like nothing in the existing catalog, and watched researchers figure out that they were something entirely new, rapidly growing supermassive black holes in the young universe, invisible to every instrument that had come before JWST. We watched the August 2024 JWST paper try to put the alarm in context, and we saw what the popular coverage of that paper got wrong. And we watched, through the big wheel and XMMVID 1-275, and the persistently elevated number densities in JADES, new anomalies arriving even as old ones were being resolved. This was not a story about the Big Bang being wrong. This was a story about what happens when science finally gets direct access to something it has been modeling from a distance for decades, and what it finds is almost always different from the model, because that is what direct access does. Even now, after nearly 4 years of JWST data, the picture is not complete. We do not know the specific physical mechanism that allowed early universe star formation to be more efficient than models predicted. We know it was more efficient. We do not yet know why. We do not know what the little red dots represent in the broader context of galaxy and black hole coevolution. They are clearly important. Their exact role in the story of how galaxies and black holes grew up together is still being worked out. We do not know whether the remaining tension in the early galaxy luminosity function requires astrophysical model updates, deeper theory revision, or changes to lambda CDM itself. We do not know whether the Hubble tension and the early galaxy problem share a common physical origin, or whether they are independent failures of different parts of the standard model. And we do not know what JWST will find as it continues to look deeper, longer, and at more targets. Given the surprises of its first 4 years, it would be overconfident to assume the next 4 will be quiet. There are a few things worth taking from this story that go beyond JWST and the early universe. The first is that the Big Bang theory is not the same thing as models of galaxy formation. Understanding the difference matters. The Big Bang is among the most robust theories in all of science. Galaxy formation models are active, contested, and being revised. Conflating the two, as much popular coverage has done, produces a false picture of both scientific stability and scientific crisis. The second is that extraordinary claims require extraordinary patience. The most alarming JWST findings from 2022 have been substantially revised by 2026. That revision is not a failure. It is the normal process of science iterating toward accuracy. The third is that unexpected discoveries often come in unexpected forms. The little red dots were not what anyone was looking for. They were found while looking for something else. They turned out to be scientifically important in their own right. The fourth is that models built without direct observational access to a domain will always be incomplete. Lambda CDM was built without direct access to the first billion years of cosmic time. JWST provides that access. The places where the model fails are not failures of cosmology, they are the invitation to do better cosmology. And the fifth is this: the most powerful question in science is not, was I right? It is, where was I wrong, and what does that teach me? JWST has given us the most precise answer to that question that early universe cosmology has ever had. So I want to leave you with a few questions tonight. What does it mean to build a model of something you have never seen directly? How confident should we be in scientific frameworks constructed from indirect evidence, however carefully assembled? When JWST shows us the early universe for the first time, and some of what it shows doesn't match the prediction, is that surprising? Or is it exactly what we should expect from the first direct look at something we have only ever inferred? And what does it say about science, about the kind of institution, the kind of practice, the kind of human endeavor that science is? That the response to unexpected data is not to defend the old model at all costs, but to immediately begin questioning it, testing it, revising it, and making it better. Sit with those for a moment. They are bigger than JWST. They are bigger than the early universe. If this story stayed with you, tell me in the comments which moment was the one that pulled you in. Was it Ivo Labbé staring at galaxies that shouldn't be there? The discovery of the little red dots, a new category of cosmic object nobody had predicted. The realization that the Big Bang theory was never actually in question, just the models built on top of it. Or the final insight that JWST has done what the best science always does, shown us where our confidence exceeded our understanding and opened the door to something better. I want to know. And if you want more stories like this, frontier science, told honestly and carefully, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. We built a picture of the early universe without being able to see it. Then we built a telescope powerful enough to actually look. And what we found, in those first images, in those unexpectedly bright and unexpectedly massive early galaxies, was not proof that we were wrong. It was proof that we were not quite right enough, which is, in the end, exactly what science is for.